The problem statement from GATE Physics 2013 reads as follows. Consider the following circuit. This circuit contains an op-amp. There are two questions related to this circuit, which are: first question, for this circuit, the frequency above which gain will decrease by 20 dB per decade is. This is the definition by the way of cutoff frequency, omega c. And the second question is, at 1.2 kilohertz, the closed loop gain is. Right. So since this is an op-amp based questions, and before we start solving the problem, we need to ask ourselves a few questions. First, is this op-amp ideal? Now, the question is silent about it. The question does not say whether the circuit is ideal or not. If the question is silent, we will assume that the circuit, the op-amp is an ideal one. Second, check if there is any feedback in the circuit or not. How do we check that? We do that by seeing whether the output node is somehow connected to any of the input nodes. So we see that this output node is, the output voltage is being fed to the non-inverting input here through this resistor. So yes, there is feedback. Now, if there is feedback, we ask whether it's positive feedback or negative feedback. How do we determine that? We determine that by seeing whether the feedback is being fed to inverting terminal, which is the negative terminal here, or the non-inverting terminal, denoted by plus sign here. We see that feedback is being connected to the positive terminal, the non-inverting terminal, and hence this type of feedback is known as positive feedback. Now, since this is an ideal op-amp, we'll assume that the current entering here is 0. Also, the current entering here is 0. Next, we know that actually in the model of an op-amp, there's an R in here. So I can write, applying Ohm's law across this R in resistor. So I can write V plus minus V minus equal to R in times the current flowing. Current flowing is 0 in ideal scenario. Usually the value of Rn is a few mega ohms. So I get V plus minus V minus equal to 0, which gives me V plus equal to V minus. Now this is a very important result that we have obtained. This is also referred to as virtual short. What this means is that the inverting and non-inverting terminal are sitting at the same potential. They are at the same potential, hence the term short. Why virtual? Note that there is no actual wire that is shorting these 2 points. No, there isn't. It's just the peculiarity of op-amp is such that it appears as if the inverting and non-inverting terminal are at the same potential, and we denote this effect by using a dashed line between these 2 points. So this denotes that these 2 points are at the same potential, not joined by a wire, just sitting at the same potential. Now, let's go ahead using this information. Now we'll go ahead and try to solve our problem. Now this is the circuit that was given to us, and I've just drawn the circuit again here, and we are required to find what is the cutoff frequency, which is denoted by omega c, and the closed loop gain at 1.2 kilohertz. Okay. Now if you look carefully, the left half of the circuit is nothing but a low pass filter. This is a low pass filter. This is a low pass filter, and the expression, and this is the general circuit of a low pass filter. Now if you see the left half, this blue rectangle resembles exactly like this, right? Let's assume that this point is Vx. The potential here is Vx. So due to the virtual short condition, the potential here will also be Vx, right? So this essentially V out is essentially nothing but Vx in this case, right? And this is the expression for this circuit. So using this information, I can simply say that Vx over Vin is equal to 1 upon 1 plus j omega. Let's define R as 10k and capacitance C as 100 picofarad. So j omega RC. This is the first result that we have obtained. Now let's look at the second half, the rectangle in blue, the rectangle in red. Now this circuit is nothing but a positive feedback op-amp resistor, and we can try to find the gain of this circuit. How? So we know this potential is at Vx, right? Because due to the virtual short, so this point will also be at Vx. Now let's try to apply Ohm's law. Note that the current flowing here would be 0 because this is an ideal op-amp. Similarly, current flowing here would be 0, and let's assume a current I is flowing through this path. So since no current can go here, all the current I has to flow here, right? So what I can do is I can write, so let's try to find the value of Vx or I. So I'll write Ohm's law across 1 kilo ohm resistor, across 1 kilo ohm. So that would be V equal to IR. So the potential across this resistor 1K is V naught, V out minus Vx equal to the current flowing through the resistor is I times 1 kilo ohms. So I get the value of I as V naught minus Vx milliamps. If you take 1K below, it will become milliamps. Now let's call this expression 2. Now I'll apply Ohm's law across 2 kilo ohm resistor, and I will write Vx minus 0 because the potential drop across this resistor is Vx minus 0 is equal to the current flowing is I times the resistor value, which is 2K. So this gives me I equal to Vx over 2K. This is expression number 3. Now 2 and 3, we have obtained the value of current in 2 and 3, so I'll simply equate 2 equal to 3. So what I can write is V naught minus Vx over 1K is equal to Vx over 2K. K and K gets cancelled. So what I get is V naught equal to 1 plus half Vx, or V naught upon Vx equal to 3 by 2. Let's call this expression number 4. Now so if I multiply 1 and 4, let's multiply 1 and 4. I'll use a different pen here. So if I multiply 1 and 4, I'll get Vx upon Vin times V naught upon Vx. I'm multiplying LHS with LHS and RHS with RHS. It will be 1 upon 1 plus j omega RC times 3 by 2, and Vx gets cancelled. I get V naught upon Vin is equal to 1.5 over 1 plus j omega RC. Omega is nothing but the input frequency of this circuit. So omega is 2 pi f. If the units of omega is radians per second, if it's hertz, then the units of frequency, the term f here is hertz, right? So this is the expression that we have gotten. I'll go to the next slide. So yeah, we have obtained that V naught upon Vin is equal to 1.5 over 1 plus j omega RC, where R is 10 kilo ohms, remember, and C is 100 picofarad. Now we were required to find out omega C or FC, the cutoff frequency. Okay, so we know now the cutoff frequency is simply when the coefficient of the real and imaginary part is the same, because cutoff frequency is defined as cutoff frequency or 3 dB frequency, both are the same terms, is defined as when gain becomes 1 by root 2 times the maximum gain. So that happens when the coefficient of the real and imaginary part of the denominator become the same. So I can write 1 equal to j omega RC. This is at omega C, so I'll get the j will not be there because we are equating just the real and imaginary part. So 1 equal to omega C RC. So omega C will be equal to 1 over RC. Now I can simply plug the values of R and C. This is 10K and C is 1 nanofarad. right? So that this will come out to be so 10 to the power 6 1 by 10. So that is 10 to the power 5 radians per second. But we were required in the question to find terms of hertz, so we'll write 2 pi fc, because omega c can be written as 2 pi fc, which is equal to 10 to the power 5. This will give me fc as 10 to the power 5 over 2 pi. Now note that the units here will now become hertz. Okay, so now we can find simply the value. We'll plug in the values here, and we get this expression. So this is approximately 6, so we'll get something like maybe 15 0.9 kilohertz. Yeah, because that the 200 by 6 is approximately 16. So yeah, so it will get 16 kilohertz approximately. So this is the frequency that we have obtained. Right, so that is the first part of the problem. So here we can see 15.9 kilohertz. So option A is the correct for question 54. Now the next part asked us to find out what is the closed loop gain at 1.2 kilohertz. Now that's very straightforward. We just put omega equal to corresponding to 1.2 kilohertz. So we can do that. So we can say V naught upon V in is equal to 1.5 upon 1 plus j. Omega is 2 pi times 1.2 kilohertz, that's 10 to the power 3. And the value of RC we had determined here. The value of RC we had determined was 1 by 10 to the power 5. Note that RC we calculated here, right? So that's 1 over 10 to the power 5. So that's 1.5 over 1 plus j times 2 omega times 1.2 over 100. So I'll calculate this value using my calculator. So that comes out to be, this comes out to be around 7.5. So I can write 1.5 divided by 1 plus j, 7.5 divided by 100. So that's 0.075 j. Now if we try to see this, the second term, the imaginary term, is less than 10 times the first term, the real term. So we can neglect the imaginary term. So we can say it's approximately equal to 1.5. We can neglect, we can in such scenarios we can neglect the real or imaginary if they are more than 10 times greater. So one is greater than 0.075. Hence the imaginary part can be neglected. Imaginary can be neglected. So the answer we get that the closed loop gain at 1.2 kilohertz is 1.5. Let's see if we have that option. Yeah, so the B option is the correct one for this. Thank you for listening.